sequences right here you just saw, and basically you have already got the first kind of formula down. You know what comes next, and you can recognize patterns a lot of times. Sometimes you can't recognize the pattern, not the end of the world, but we're going to talk about specific situations where you absolutely should be able to recognize the pattern. So, for example, in this one, the next number in this sequence is 10. Then 12, 14. Right? How do you get to the next term? Just keep adding 2. So this sequence, the next term in the sequence, 25. And how do you get to, you add 5. All right? Now there's 2 ways to get to these terms of the sequence. What's one of the ways? Pardon?
Squaring 1, squaring 2, squaring 3.
So square 1, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared.
You add up to like every time, so it goes 3, then plus 5, then plus 7, then plus 9.
Plus 3, plus 5, plus 7, plus 9, and you can continue on that way. This sequence, you want to make sure you recognize when you see it. Okay? It's not one of the two main types of sequences, but this one, the perfect squares, where you might be looking at it as 1 squared, 2 squared, 3 squared, 4 squared, you want to remember that sequence when you see it. You know that they are squares. Right? So what's next?
125.
216. And this sequence are perfect cubes. 1 cube, 2 cube, 3 cube, 4 cube, etc. You want to recognize that sequence as well. There won't be many sequences that are not of the type that we are most likely to work with, but these 2 right here would be 2 of them. So recognize your perfect squares, perfect cubes. If you know the next sequence, you can give one answer and that's it. And then if you could not give it away, that would be better for everybody else. If you know what comes next, you can say the next term, but then let everybody else have a chance. So what's next? What comes after F? Again, you get to do 1, and that's all. I mean, it's really great that you know this. Don't be sorry, but let other people have a chance. What's next? What's next?
E.
What is it? Ready to do the touchdown dance. I will tell you, the people who know it, obviously it's obvious. Anytime you have something explained to you, it becomes obvious. But every person in this room knows what comes next. Every one of you knows this sequence. And it is, in fact, the first thing you ever learned in mathematics. Every single one of you knows this sequence. It is absolutely the first thing you ever learned in mathematics. What's next? D. The first thing you learned in mathematics. Some of you learned them with Cheerios or M&Ms. The first thing you learned in math? Not the first thing you learned in math. The very first thing. That's what you need to think about. Yes, you do.
Wow. Why is it not said?
All right. So
Obviously, you got that.
when we look at a sequence, you're looking at an ordered list of integers. Now you're looking at an ordered list, and there's two things that we're concerned with in the sequence. The members of the sequence and the position each term is in the sequence. There are two kinds of sequences. Finite sequences are sequences that have a last term, and infinite sequences that do not have a last term. So if at the end of your sequence you see dot, 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 and nothing after the dots, then it's infinite. If you see a last term with no comma, then it's finite. The position of the term, this is the first term. 2 is the first term, 4 is the second term, 6 is the third term, and 8 is the fourth term. You are going to be very aware of the position that the term is in and what the term is. We talk about, you don't need to really worry about this being domain of range. A sub 1 is the first term. A sub 2 is the second term. A sub 3 is the third term. A sub 4 is the fourth term. That's how you'll identify the terms in general. A sub 1, A sub 2, A sub 3, A sub 4. The terms themselves are 1, 2, 3, 4. Potentially. Like in this one, A sub 1 is 2, A sub 2 is 4, A sub 3 is 6, etc. So the domain is the position for 1, 2, 3, 4, and A sub n are the terms themselves. So you could actually write an ordered pair, position, comma, term. Okay? So we would write the ordered pair as position, comma, term, if you wanted to have ordered pairs. We're not very often going to be working with them in ordered pairs. We do, however, want to be able to identify any term in the sequence. Any term can just be identified as A sub n. So we're not saying A sub anything in particular, just some unknown position. We're going to be concerned with coming up with a rule that will generate our terms of our sequence. This would be considered a rule to generate your terms. A sub n is the term you're looking for, and n is the position. The first term in this sequence would be A sub 1, and you can find it simply by putting in a 1 where the n is. So A sub 1 How do you find a sub 2? Yeah, plug in a 2 for n. So if you want to find a sub 2, you're going to be 5 times 2 minus 1, which is 9. So the first 5 terms of the sequence are going to be 4, comma 9, comma 14, comma, and 24. And once you recognize how the pattern works, you don't have to keep using the formula to generate the terms. When it's quote-unquote obvious for you, then you're absolutely welcome to stop.
So technically, we don't have to do like 1 or 2 times.
Well, 1 probably isn't enough because there's other kinds of sequences besides this type of a sequence. And you'll see that not today, but in the future. You'll just have to trust me. Everyone okay on how to generate the terms of a sequence from the formula? So this sequence is not the same as the last one, but we can still generate the terms. So a sub 1 is going to equal -1. A sub 2 is going to equal 2 squared minus 3. So a sub 2 is 1. Now you have to be careful that you don't just keep adding 2 per se. You have to just be really careful with these because this is not multiplication, this is a power. Now, you'll notice though, because it's a power of 2, that things work out pretty well. 2 to the 3rd minus 3, you're going to get, how much? 5. But this time, again, it's not just plus 2, plus 2, plus 2. It's a little bit different. So when you look at your sequence, you might be saying, oh, well, yeah, it's going to be -1, 1, and then you might go to 3. But 2 to the 3rd is 8. Minus 3 is going to give you 5 for the 3rd term. So the 4th term is going to be 2 to the 4th minus 3, which is 13. Now, can you find a pattern? Yeah, I bet you could find a pattern somewhere in there. And that pattern is going to have to do with powers of 2. You added 2, then you added 4, then you added 8. What do you think you're going to be adding next? 16. So you're probably going to get 29. I don't know if it's always worth trying to generate a pattern, but recognizing the pattern, there's definitely going to be a value here. So when we do a to the 5th, you're going to have 2 to the 5th minus 3, and 2 to the 5th is, used to be 64, but then after the math revolution, it became 32. So then we're going to get that. See how important that math revolution was in history. We don't want to forget that. So there are the first 5 terms. Everybody with me so far? Everything we're talking about right now is in a very general sense. See if you can find the first 5 terms of this sequence. All right, let's take a look at the 5 terms you came up with. Philip, what'd you get for the first term?
1 over 2.
And you're going to want to write these as fractions. Thank you. Where would I be without you? Still wouldn't be here today. The red marks are there. Philip, what'd you get for the first one? 1 over 2. Raven, the second one?
2/3.
2 over 3. Jonathan?
3 over 4.
So you start to see a pattern developing here. Haley, the next one?
4, 5.
Got a girl? Kamal?
5, 6.
Nice. Decimals are typically not your friends with this. Can I get you a pillow, blanket, anything? Me too. Maybe we should have like some graham crackers and warm milk, and I'll take a nap.
No, it was really weird. Okay, I couldn't sleep at all last
Me
night.
either.
I was at school, I could sleep.
Oh, isn't that amazing?
Yeah.
So where you want to be is the nurse's office. Beds, blankets, and pillows down there. Okay, then you're going to need to put the head up and just pretend, you know. You're killing me right now. Describe the pattern in which the next term, describe the pattern, write the next term in a rule for the nth term of the sequence. All I want you to be able to do is describe the pattern right now. The rules for problems like this, I don't care about. You got it?
Yeah.
What is it?
+3, +5, +7, +9.
So you're adding consecutive odds, what do you say, odds? 3, 5, 7, starting with 3, and you're going to continue to add a consecutive odd. And I'm not interested in rules for the next term in the sequence. I just want you to see, oh look, +3, +5, +7, so the next one is +9, and so forth. Okay? It was so sincere, I'm sure it meant so much coming from you. You're the man, just throw it right on that table. I'll make it pretty tomorrow. Thanks.
You should bedazzle.
I'll let you bedazzle. I won't be bedazzling. Okay, take a look at this one. Taylor, how do we get from place to place, from term to term? So it's all the same on this one. Now that one we like. And we're going to want to come up with a way to identify that term, and we're going to come back to that. So I want you to do pattern recognition now. We got it. Now we want to come up with how do we get this rule. So we're going to use this sequence to generate this. This is called an arithmetic sequence. Okay? Arithmetic sequences mean to get from one term to the next, you're going to add the same thing over and over and over again. And that's what we're doing. We're adding -4. We're subtracting 4 to get from one term to the next. Maybe you're not going to be finding those rules today. No, it's not. It's easier if you know how to do it. Now you're just okay? So how do we get to the next term in the sequence, or the next term in this sequence? How are we getting from one term to the next? +5, +7, +9. So again, you're adding consecutive odds to get from one term to the next, starting with 5, starting with adding 5. Really, that's all I want you to be able to do at this stage of the game. Some of these sequences are arithmetic, some of them are not. Some of them are geometric, some of them are not. It doesn't matter to us today what kind of sequence you're dealing with. Now, the graphs, you don't have to worry about those. But you do have to learn this notation. This is called series or summation notation. This capital Greek letter E. Okay, that's a capital S actually in the Greek alphabet. It's called sigma, and it's usually implies when we use this notation that you're finding the sum of a sequence, or more likely you're finding the sum of a series. And a series is a sequence where you replace the commas with pluses. So your sequence 2, 4, 6, 8, as a series becomes 2 plus 4 plus 6 plus 8. Now, at this stage of the game, if you want to find the sum of the series, you're going to add the terms in the series. That's what you're going to do today. We'll teach you formulas for certain series and sequences tomorrow and the next day and the next day. But right now, we want you to literally take out your calculator right now. Summation notation is a way for you to write down the sum of a sequence or the sum of a series without writing all the terms of the series down. So you see they have the sigma. You'll have a variable on the bottom. That variable in this case is I equals, and then it'll be a number. And then on the top, there'll be another number. The variable can be anything. But whatever variable is on the bottom will appear in this little formula out here. So if this is I equals 1 and this is 2I, you're going to start by plugging in a 1 for I. If I equals 1, you put in a 1 for I, what do you get? 2. The next number greater than 1 is 2. You plug in a 2 for I, and you get 4, the second term of the sequence. The next number for I would be? No. The next number for I will be 3. When you plug in 3 for I, the third term is 6. The number on the top tells you when to stop for I. It tells you the last thing to plug in for I. When you plug in a 4, that's where the 8 comes from. When you see this sigma, your answer is one number. When you see sigma from 1 to 4, they're asking you to add all these up. And when you add them, you get, what is it? 20. This next question is this question after that I'm going to ask is a trick question. What kind of a series is this one right here? Infinite. Can you find the sum of an infinite series? This is the trick question. Okay, so if it was a trick question, and I told you it was a trick question, and your initial response was, hi. Welcome back. You will know, but when you're standing up, you're going to try harder. You get 2 free ones, that's it. Now, you're going to stand on the third one. It'll help immensely.
Really?
All right, so,
Rachel, I will drool on you.
Ew. What? Gross.
okay, first of all, take responsibility. You're the one who has the issue. Stop. I will bend as light as I can about it, but you will stand on 3. If it's an infinite sequence, you can find the sum of some infinite sequences or series. So we'll talk about that as we progress through. It is counterintuitive. If you're adding an infinite number of things together, it would feel like an infinite number of stuff. It has to be infinite. And for the most part, it is. Remember, this goes on to infinity. 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14 plus 16 on to infinity. There's no sum for this. Because you're going to keep adding and adding and adding and adding, and it's going to have no sum. Okay, it's going to get bigger and bigger and bigger. If it's a finite series, there's always a sum. So this series right here is finite. And I guarantee you that if you find the sum of this series, that some of you in this room will do it wrong. Okay, so take a minute right now, pull out your calculator, and just see what you get when you add up these numbers. 829. Parker, what'd you get? Attaboy. Lily, what'd you get? I don't need 2. Arthur, what'd you get? 2025. Let's see what else we got. Parker, you got one of these 3? Taylor? Ooh, that's a popular one. Rachel? Then answer me why. So again, you have a calculator and you literally don't understand how to add numbers on a calculator. Is that what you're telling me? Then you need to go somewhere else. You added what you see, right? Yeah. And that makes perfect sense. 64, 1, 8, 27, and 64 is 100, plus 7, 29, 8, 29. It's a very logical set of circumstances for us. But it's not right. Who got the 1682?
I forgot to add 7 times 7.
7 times 7 times 7? You mean 729?
No, 7.
Oh, you just skipped the 7 cubed one?
Yeah.
Okay. So you were, did you do that on your calculator, like, without writing anything down? And you just worked them?
No.
You did write them all down?
Yeah.
Okay.
Not all of them. I just like this. Yeah.
So some of them you did, some of them you did. Okay. And the 2025, how did you get that? So you recognize this as one of those patterns we had on maybe the first slide?
Yeah.
And this is the sum of a cubes. And this part right here is the problem part. That dot, dot, dot. What does the dot, dot, dot mean? It means 2 things.
In between there's more than that. There's more in there,
Okay?
but we're just not going to list it out for you.
Okay? Or, no, it doesn't mean there's a pattern in this case. But what is the other use of dot, dot, dot? It's going to infinity, and in which case they wouldn't put anything, the plus 29 wouldn't be there. It just continues on in the same pattern. But it goes to infinity. So once you recognize that they're the cubes, your goal is to find the cubes. 1, 8, 27, 64. What's after 64?
125.
125, which is not shown. After 125, 216, which is not shown. After 216, 343, not shown. 512, not shown. And then your 729, which is shown. The dot, dot, dot is math world. And mathematicians are lazy. So they're constantly trying to find a shortcut way to do this. How do we find the sum? You bang on the calculator. There's just nothing else for you to do with this sequence. Now, there are ridiculous formulas for this sequence that maybe you could figure out the sum for. It's just not worth it. It's so much faster to do this. What we do need to be able to write, though, is we need to be able to write that series, that summation, using sigma notation. Now, go ahead.
We need is 9 on the top,
9 on the top.
then I equals 1 on the bottom.
I hate I. You know why I don't like to use I? Because it reminds me of the imaginary number too much. I'm going to intervene here. Since it's my board, I'm going to write in. But you can stick with I. I'm not really trying to talk you out of it.
N equals 1.
And so we're going to go from when n equals 1 to 9.
And then on the side you do n cubed.
Cubed. Perfect. Now, there are an infinite number of ways to write the summation for that. I would encourage you to try to stick to n equals 1 to whatever you're going to. But we could, and I always have students in the past, oh, I just don't like starting with 1. My favorite number is 3, and I really want to start with 3. So I'm going to go from n equals 3 to 11. And I'm going to do n minus 2 cubed, just to be difficult. Oh, that's just fine, but the creativity thing is going to be an enemy more than a friend. There's no reason to do this.
You only use 4 numbers.
For n,
Yeah, because it's like n cubed, so couldn't it be like 1.5?
1.5.
And like, just like
Oh, you're talking about from here to here? You mean like from 3 to 11, I wouldn't pick 3.5, right? Yes, that's absolutely right. You're going to go by this tells you how to find the first term. When I plug in a 3 here, I'm finding a sub 1. When I plug in a 4, I'm finding a sub 2. Here, when you plug in a 1, you're finding a sub 1. So positions are integral locations. Now, these numbers, top and bottom, are typically integers. I don't think I've ever seen them be fractions. Maybe they could be fractions, but I cannot recall a situation where that happens. So that's a pretty good question. Again, being creative, go down to Owens and take a ceramics class. Here, we want everybody to be boring old clones. If I could play the tape over again, I said we're just going to skip the graphs because it doesn't. You can. I think you can graph them if you want. It's just not that important today. Right now, I want to finish going through this. If that's okay. Now, this sequence, you notice that you have fractions in 3 of the terms, but not one of them. I would encourage you to make all of them be fractions. So this 1 right here, make it 1 over 1, plus 1 over 2, plus 1 over 3, plus, sorry, why am I doing that? 1 over 2, 1 over 4, and 1 over 8, plus dot, dot, dot. So if we're going to write the series using summation notation, again, I'm going to keep it simple and go from 1. What goes on the top? Infinity, because this time, the dot, dot, dot at the end doesn't mean that there's terms in the middle. It really means that it goes to infinity. What's the little formula that's going to generate it?
n plus 0 over 1.
Once again?
1 plus 0 over 100.
Say what you were going to say.
I was going to say 0 over 1, but that doesn't work.
Well, you said 1 plus 0.
N plus 0. That's what I said.
Okay. I misheard you because the first thing that came out of your face
I only
sounded
looked
good.
at the 2 first terms.
Huh?
I only looked at the 2 first terms,
Okay.
and then I realized I needed to look at all 1.
Okay.
Let's see, 1 over n.
1 over n.
But that's more, because if that's good.
Okay.
Is it 1/2 n?
1/2 times n?
Yeah.
Like this? Philip?
Yeah.
So when n is 4, the fourth term, 4 times 1/2 is 1/2 times 4.
2.
Are you sure? Because you don't have to look like you're sure that half of 4 is 2. Okay, you're not listening to me. You're thinking about this problem. I just want you to listen to me. 1/2 times 4 is 2. We need it to be 1 over 8. So that's not going to generate 1 over 8. Riley? I'm not, never mind, I'm calling on you.
Well, I had another option.
Where did you drop it? What do you think?
Well, like, it's like 2 n. No.
What, do you mean 2 times n?
Yeah.
You have it.
What you're saying?
Yeah.
Yeah, but jib it, Parker? What is it? Like this. You know that was all out loud.
You don't win anything.
Welcome to the Price is Right. So what you're looking at on the top, they're all ones. You better have something like 1 over, and then you're just looking at the bottoms. 1, 2, 4, 8. Those are powers of 2. So when n is a 1, 2 to the first is 1 over 2 is 1 over 2. We need it to be 1 over 1. You could, but again, I wouldn't encourage that. So if we started with 0, that would be great. The problem with starting with anything other than 1, which again, I'm not selling it, but when you start with 1, you always are finding the first term. If you start with 0, you'd be finding the first term, but sometimes it's confusing. Again, I'm okay with it. That's a great observation. How could I leave the 1 there and still go with a power here?
1 over 2 to the in parentheses n minus 1.
So just subtract 1 here.
Yeah.
And that way you'll drop down to 2 to the 0, which gives you 1 over 1 in the first spot. When you go to the second term, 2 minus 1 gives you 2 to the first. Third spot, 3 minus 1 is 2 squared. So you had it, but you got to be careful with where they start. Sometimes they're going to start you on this term, 1 over 4. So when you put a 1 here, you just have to be careful to make sure that it's n plus 1, if this is where we were starting. Recognizing the pattern today is more important to me than dialing in on this. We'll clean this stuff up in the next few days. Okay? I want you to find the sum of the series generated by this sigma notation in this sigma notation. Use a calculator to find the sum. And when you added them, what did you get? You mean 120? No, you went 120? Are you sure it's 120?
I missed the beginning of the lesson a little bit.
We noticed that. We're glad to have you back. But when you added these up, you got, say it again, 120. Anybody get a different sum? 123. Anyone get a different sum from that? How many other people got 123? She just wanted to raise her hand. So I'm thinking you got a 6, a 4, and a 2. Yeah, I'm just not seeing in an 8. I don't think you're going to end up with a number that ends in a 3. This calculator usage, brutal. You know what? Hate it when that happens. Let's talk about how many numbers there are in the series. You can write this down. It will really help make a difference. Take the top number on top of the sigma, subtract the bottom number. Top number minus bottom number plus 1. top number minus the bottom number plus 1. If you follow that, that'll tell you how many terms you're going to be having in the series or the sequence, in the sum. So on this one, it's 5 minus 1 is 4, plus 1 is 5. 1, 2, 3, 4, 5 terms. Okay? Robin, what'd you get for the terms in this second one?
20,
20?
40, 68.
Anything else? Anybody get different terms?
101 and 148.
Okay. So how did you find the first term? Okay. And how did you find the second term? Excellent. And how do you find the third term?
Third term is 5 for K.
Okay. And are we supposed to plug in any other values for K? You start with K is 3 and end when K is 5. The 5 does not tell you that there's 5 terms. 5 minus 3 is plus 1, 3 terms. The first term we find when we plug in the 3, just like you did. Okay? The last term you find when you plug in the 5. That's the end of the sequence. 20 plus 41 plus 68. Okay? Grace, what'd you get when you added them?
129.
Anyone getting a different sum? Jonathan? Jackie. So, you can copy these formulas down if you want, but I just can't, I cannot remember formulas for special sequences. So you do whatever you want. If you want to memorize them, there they are. So if somebody says, what's the sum of the first 50 integers, positive integers? 1 plus 2 plus 3 plus 4. Here's your formula. But we have better ways to determine that. The sum of the squares, well, that's a special formula. The sum of the n terms of 1, I just don't get it. Why would you want to memorize those formulas? I don't know. So if you want them, you can take a minute and copy them. They will not help you even a little bit. Okay? You'd be much better off just adding them up like we just did. But go ahead. Anyone still copying? Zero credibility in the room. Zero. It's okay. It doesn't get any better next year. I still have no credibility. What's that? People don't believe me. It's all right. Of course I can't. Plug in a 3 for K. What do you get? How'd you get 81? Minus, which is? That's how I got the 20. The next number after 3 is? Plug in 4 for K. 48. Right. And then you plug in a 5 and stop. 5 would be the last one. Start with the bottom number, end with the top number, put all the integers in between. Okay? So, this is a type of application problem that has got a pattern to it. And you have a layer of apples. They're calling the top layer the first layer, which to me just sounds silly to call that the first layer, because it seems to me that would be the last layer, but oh, I know. You have a stack of apples. How many are in the first layer? How many are in the second layer? 4. How many are in the third layer? In the fourth layer? Sorry. Okay. Now, how many are going to be in the last layer if we're only going to say 8 layers instead of 7? 64. So that's a way to write that series without having to write down all of the terms of the series. The first thing that it's asking you to do is to use the summation formula. So I want you to write it as a summation from n equals 1 to 8. What's the formula that will generate the terms of the series? What's the formula that will generate those? Not cubed, and squared. Right? These guys are all our perfect squares, so it's simply n squared. Now, how do we actually find the sum? We're just going to add it up. We're going to go 1 plus 4 plus 9. So in that case, we may want to go back and say 16, 25, 36, 49, 64, so that you can see all the terms of the series. And then pull out your calculator. How do you add them? Bang away. Now, Raven's not going to do that because he has a formula. He'll have that thing memorized by tomorrow. What? The formulas don't? This is the formula that's going to apply right here. That's the sum of the squares formula. Knock it out. But we'll be done by the time you figure that out. What's the sum equal? So that means you need 204 apples to make this stack. I'm sure the kid in the grocery store is figuring that out as we sit here. Mr. Johnson, I need 204 apples to make that stack. There's only 203 here. What do you want me to do? It's not going to look right. All right, so this is what you're going to work on tonight. You do not need to worry about the graphic. Okay, I don't really care about